Okay, we will start lesson 6.2 about the confidence interval for one mean. In lesson 6.1, we covered this confidence interval for one proportion. Okay, this is the setup for the case of one mean. Consider a random sample of size n, where each random variable, where we have an random sample, it's 1 until let's n IID random variable from a population distribution with mean mu and variance sigma square. Okay, and we will have three main characteristics. The first one is the population distribution might be normal, but it might not. The second one, and is the most important, is the population variance might be known or unknown. Here, the population variance is sigma square, remember that. And the sample size might be large or small. Okay, we would like to estimate mu, that is the population mean. I mean, we have this population with mean mu, and we would like to estimate it. The point estimator for mu that we already covered in week 5 is the mean, the sample mean x bar, right? We have that the sample mean x of n is equal to 1 over n times the sum of the random variables. That is the estimator, and the estimate is just the lowercase x bar, that is 1 over n of the sum of the data. Okay, the first case that we are going to cover is when the population variance is known. It's something that is not very common, but it's important to cover it, and we will understand how to do it. Okay, the sampling distribution of x bar. So remember that we have the central limit theorem, that if n is large by CLT, we will have that x bar is asymptotically normal. That means for a large sample size, it's normal with mean mu, that is mu is the expected value of each of the random variables in our sample, and the variance is going to be equal to sigma square over n. And this sigma square is the variance of each of the random variables. If the underlying population is normal, this sampling distribution is exact for any n. We will need the condition that n is large when the population is not guaranteed to be normal. If it is normal, then it doesn't matter the sample size. So we have this distribution here of x bar. And the distribution of x bar, the PDF of x bar, is normal, and the mean is going to be mu, right? And we will have here 1 times the standard error, that is, in this case, the variance of x bar is sigma square over n, so we will have here mu plus sigma over square root of n, and we will have here mu plus 2 times sigma over the square root of n. Remember that the standard error is the square root of the variance, so it's sigma over the square root of n. And here we have mu plus 3 times sigma over square root of n, and we have the negatives. Sorry, it's mu minus sigma over square root of n, mu minus 2 sigma over square root of n, and mu 3 sigma over square root of n. Okay, the standard deviation of x bar, remember that is also what we call the standard error of the sample mean, is sigma square over n, just to make it more clear, sigma over square root of n. Okay, this is the PDF. So what we are going to do here is the same, is analogous to the case of the one proportion. So we start with the interval that its bar has probability 1 minus alpha of being in. So this interval is given by, in general, remember that is mu, its bar is going to be with probability 1 minus alpha between mu, because it's the mean, mu minus z of alpha over 2, this critical value, times the standard error, that is sigma over square root of n. And the same for the other case, but in positive. The critical value and standard error is sigma over square root of n. Okay, remember that this c is the critical value. Then, similarly to the one proportion, we invert the interval to get mu in the middle. So doing the algebra there, we will have that here we have x bar minus c of alpha over 2 times sigma over square root of n, going to be less or equal than mu, less or equal than x bar plus c of alpha over 2, the critical value, sigma over square root of n, and this probability is the same. But keep in mind that this mu is unknown, is our parameter, but it's a number. And here, this x bar is a random variable. It's expressed as a random variable. But when the random endpoints are our estimators, and when we plug in the data values, it's 1 or 10, to obtain our confidence interval estimate. So remember that if we put these numbers, if we replace in the equation these numbers, then we get our estimate.